Hi, this is Dr. K. I wanted to take you through the pre-lab for experiment 14A. This is our first synthesis laboratory, and we're going to actually make a ester, and this ester is known as isopentyl acetate. There's a very nice essay on esters and fragrances in your textbook, and you should probably read that for background information. So, the main reaction for the experiment that we're doing is that we're going to be reacting acetic acid with isopentyl alcohol. We'll heat it and then do it under acidic conditions. And this is an equilibrium reaction, and what we'll eventually make is isopentyl acetate. This process takes about an hour to an hour and a half of the lab period. Most of these steps that we do in this experiment can be finished in one lab period if you work efficiently. Now, just so you know, this is an equilibrium reaction, and to drive the reaction to the right, what we're going to be doing is adding an excess of acetic acid, hopefully using up most of the isopentyl alcohol. What's left at the end of the reaction, because it's an equilibrium reaction, is a mixture of all the things that were put into the conical vial plus the product, and hopefully the product will be the majority of that. The reason that we use isopentyl alcohol as the limiting reagent is because the alcohol turns out to be very difficult, or can be very difficult, to remove from the acetate, because they have a lot of similar characteristics in terms of their hydrophobic regions. And as a result, if we can minimize the amount of that in the synthesis that's left at the end, then there's a little less purification that has to go on at the end as well. So, there's usually 3 steps in one of these synthetic reactions that we do, or synthesis labs, or prep labs as we would call them in organic chemistry. You're going to make the compound. That's what I just described. Acetic acid, isopentyl alcohol, acidic conditions, heat it, and then produce the product. Then there's the working up of the reaction. Now, the working up can be a lot of things to a lot of different people. In many reactions, we have to stop the reaction. Now, this is an equilibrium reaction, and hopefully we get to equilibrium. So there really is no stopping the reaction in this case. But sometimes we have very reactive reagents that we use to produce a particular product, and those have to be removed safely to prevent any kind of dangerous side reactions as we work with the product material. The second thing that we often do is we isolate the product from the junk that's left over. So this isolation involves a crystallization of products sometimes, and extraction, which is what we'll be doing in this experiment, and sometimes evaporation or sublimation. Now, having said all that, usually the first isolation is not very pure. And so a third step that happens in the workup portion of the experiment is purification. In this particular lab, we'll use distillation, but you guys have already used recrystallization in earlier labs. The final portion of an experiment is the characterization. How do you know what you got is what you got? So, in our experiment, we're going to do that by infrared spectroscopy. That'll be a new technique, and it's at this point of the semester mostly about getting used to the equipment and very little analysis, but I will point out some of the key characteristics of that in class. The other thing that we'll be doing, and this will be the major component of our characterization, we'll be doing GC mass spec and looking at the mass spectrum of the product to verify that in fact we have isopentyl acetate. So the first part of this experiment is setting up the reflux apparatus. The reflux apparatus consists of a conical vial in an aluminum block. So this is the conical vial. There's the aluminum block and some sort of condensing column. And I always recommend that you use a water-cooled condenser because it provides the most efficient method of capturing any of the gases that are produced by the reaction. Remember, unlike a distillation, in this particular experiment, when you do a reflux, your goal is to leave everything in the conical vial. When you do a distillation, your goal is to push some of that material out and collect it somewhere else. Well, if we push stuff out too early in a reaction, then what ends up happening is the reaction doesn't proceed successfully because some of your reagents are gone. So the idea is we'll heat the reaction mixture until it begins to boil. Once it begins to boil, you'll notice somewhere up in the column a ring of liquid that forms that we call the reflux ring. Try to keep that reflux ring in the bottom portion of the condensing column. The reason you want to keep it in the bottom portion is because that represents the condensing liquids from the reaction mixture, and you want to make sure that these liquids condense in the lower part and then return back into the conical vial. If that's not happening, if the reflux ring rises or you start to smell a lot of vapors coming out of your reaction, then what you need to do is lower your temperature of your reaction. That's kind of the double-edged sword, because really what you want to do is get the reaction hot and allow for the reaction to proceed to completion or towards completion as much as you can. But at the same time, if you make it too hot, bad things can happen, like loss of product or decomposition of product or loss of material during the reflux. Now, a very important point to make is, what's the temperature you have to set this at? Well, it's a boiling solution. The temperature of the aluminum block is not important. What's really important is that you look at the solution, and inside the solution you'll see little bubbles forming. That's boiling of the solution. One other thing that I need to point out is at the bottom of this conical vial you need a spin vane. The spin vane acts as a boiling stone and also allows you to mix the solution very efficiently. If you have problems with heat, then what we need to do is we'll put a blanket around the aluminum block, and I'll show you how to build one of those out of paper towels and aluminum foil. So again, temperature is not important. You don't want it to be too high. Start with the hot plate on a relatively low setting, probably 3 or 4 or 5 at the most for the small hot plates, and probably 3 or 4 at the most for the large hot plates. It'll go directly into aluminum block and you'll heat, and this process goes on for at least 60 minutes. So I would recommend that you come prepared to do something else during that time. Like I was talking about, you can spend some of your time answering the questions at the end of the lab if you've written those into your notebook. Now, when the reflux is done, what you need to do is let it cool. And then what you're going to want to do is remove the acid that's in the mixture. The acid is the catalyst for the production of the product, but it's also the catalyst for the decomposition of the product back into the reactants. Now, when the reaction's cool, that reaction is much slower, even in the presence of a catalyst, but you have a limited amount of time to get that junk out of there. So what you're going to be doing is you'll be working up the solution with sodium bicarbonate. Strong bases are not generally recommended for the workup of esters because it leads to their decomposition and reformation of the original products, and it's called base catalyzed hydrolysis of an ester. You might want to look that up in your book. Now, so water, it turns out, is more dense than the isopentyl acetate. So when you add water into this mixture, so let's say in this first conical vial, this represents your product. You're going to add bicarbonate solution. The bicarbonate is predominantly water. It's only usually about 5%. What's going to happen is the bicarbonate is going to form. There's going to be 2 layers formed in the solution. The organic layer is the top layer, and the aqueous layer is the lower layer. Now, you should verify that by looking up the densities. Those are some of the types of data that you need in this experiment. If you're going to do an extraction, you'll need to know what the densities of the liquids are, and keep that in mind for future laboratories. A couple of notes on adding bicarbonate to the reaction mixture. Sodium bicarbonate, if you remember from general chemistry, when added to an acid, produces the salt of the acid, the sodium chloride or the sodium sulfate or whatever the acid is, and then also CO2 and water. Now, we don't want to keep water in here. That'll actually go out in your aqueous phase. But we also got to be careful with the carbon dioxide. If you add sodium carbonate to the solution, or sodium bicarbonate to the solution too quickly, the bubbles that form will actually push the product out of the reaction vessel, because it'll get underneath the organic layer, it'll fizz, and those bubbles will just push everything out. So what we do is this. You add a little bit of sodium bicarbonate, and then you stir it with a microspatula. Okay, sodium bicarbonate solution goes in, microspatula spins the same way you did when you did the recrystallization. The bubbles form, they stop forming. Add a little bit more bicarbonate solution, spin it again, the bubbles will form and stop forming. Now what the book says to do at this point is to cap it and shake it. And I've never liked that method because these caps never seal that well, especially under pressure, and then when you open it up, any liquid that's in the cap comes squirting out the sides. So actually what I prefer to do is to take a pipette like this one that you use for extracting and squeeze once you've put the bicarbonate in and partially neutralize the solution, squeeze it in and out real vigorously to inject the solution in and out of the conical vial. That will mix it much better than shaking it in the conical vial. The only drawback to this kind of technique is it also introduces air, which may be a problem in some organic reactions, but it's no problem in this particular reaction. But you can use the pipette to squirt in and out solution of bicarbonate and isopentyl acetate into the conical vial for the mixing. You'll extract the aqueous lower layer, discard it, and then what you'll end up doing is repeating this process several times, but make sure that you follow the procedures that I just outlined. Add a little bit, stir it, add a little bit, stir it, and then pump it a couple of times with that pipette to get it well mixed. So let's say that you've done that and you look at your conical vial and the only thing that you have left is the upper organic layer and you've extracted the lower aqueous layer. You can very easily look in your isopentyl acetate and determine whether or not you need to do a lot of drying or a little drying with sodium sulfate. If you look at it and you see a lot of bubbles in there, those bubbles are water, that is liquid bubbles. And those, especially their water, if they're stuck to the sides of the glass, because the water and the glass are very water is very adhesive to or cohesive to the glass, and so it ends up, you can see these little bubbles stuck to the sides. As I instructed some of you in the previous extraction lab, the simplest thing, rather than to dry all that, is to simply use a pipette, suck up the organic layer, a dry pipette, and put the liquid into a dry conical vial for distillation. Before you do that, put it in a dry conical vial or a dry container, and then add your sodium sulfate to that to dry it. Next, you'll remove your product from the sodium sulfate, and then you'll end up distilling it. Now, the distillation is relatively simple. You're going to do, again, put your sample in a conical vial, but now we're going to use what's called a Hickman head. The water condenser is used simply to capture vapors and to prevent some of your product in case you overheat it or in case it bumps from going out the top. By the way, this liquid does have a tendency to bump. When you do the distillation, hot gases will rise up from the conical vial and cool in this space. Now sometimes, and this is a weird thing, sometimes it won't condense onto the sides of the glass even if you cool it with a paper towel. And what I found works quite well to get that condensation started is I remove the drying tube and then I just blow cool air in this Hickman head with a pipette, and that will cause the condensation. And once the condensation starts, it seems to be okay. Now the condensate is going to collect at the bottom of the Hickman head, and your goal is to extract that with a pipette. So what you'll do is have a clean pipette, you'll remove the cap of the Hickman head, and then you'll put the clean pipette into the solution and extract whatever distillate appears down there. Now, the goal of this distillation is actually to remove isopentyl alcohol, I should say isopentyl acetate from the isopentyl alcohol, which has a higher boiling point. One of the things to remember when you do a distillation is never distill to dryness. That is, make sure that you leave some liquid down in here. If you don't leave the liquid down in the bottom of the conical vial, basically you're going to transfer everything from the conical vial to the Hickman head, and you'll be collecting impurities in your Hickman head. So try to distill all that as much as you can, but make sure you don't take maybe the last third of the liquid that's down there if you want it to be really pure. The other thing is to make sure you distill slowly, so you can capture, get as much separation as possible from this simple distillation. Okay, now the last thing. At this point, you'll have collected your clean isopentyl acetate into a pre-weighed vial. That's what you'll be transferring to from the Hickman head. You'll weigh the vial again. You'll get the mass of product produced. You'll have to use a percent yield calculation in your notebook to figure out what your percent yield is. And then what you're going to do is you're going to turn in your samples. There's several ways that I want the sample turned in. The first one is just to create a sample vial, that pre-weighed vial. You just put a label on it according to how they specify in the lab manual, and where you can find more instructions on that is on Blackboard in the note on labeling samples on this particular experiment. The other thing that you'll do is you'll turn in, after you weigh it, a 200 to 400 fold dilution of the isopentyl acetate in methylene chloride, CH2Cl2. Same procedure as before. You'll add a ml of methylene chloride and a drop of isopentyl acetate, and then mix that well, and then transfer that to the GC vial, 1 drop or 2 drops, and another ml or 1.5 ml of methylene chloride. That'll give us approximately a 200 to 400 fold dilution to put it in the range of detection for the GC mass spec. You'll turn that vial in just like you did for earlier experiments and type your file name and file description will be written in your notebook, and I will run the GCs on the evening that you finish the experiment. And finally, you'll measure the infrared spectrum and compare that to the book spectrum. I will show you that on the day of the experiment, how to do it and what things to avoid. If you have any questions, again, feel free to email me at my email address.